about 40% of the material will cover this. But anything which is covered here also plays a role later. And so sometimes I will go into topics which are already from the material after the second midterm, because we can combine things now. You have not yet got a review sheet there in the back. Grab one. And we start, as usual, we start with geometry. And some of the things you have already seen, but it's just the idea is to get through everything so that you remember all the stuff. So vectors, you are now very familiar with vectors. You know they are defined by 2 points in the plane or in space, and we can place them anywhere. It's useful to have this feature. And we can add vectors. We just add the components, or we subtract the components, or we scale the components. And we can also form products. One of the important products is the dot product, which you have seen a lot until the very end in Stokes' theorem, when we do flux integrals, for example. And so this is the algebraic definition. And very important, we can use this dot product to compute angles between two vectors. And so this is the angle formula. It was just solving for cosine alpha. And it also allows us to compute lengths. So both lengths and angle can be expressed using the dot product. And also we can figure out whether two vectors are perpendicular to each other. So that's the easiest way to find out is with a dot product. And then we have seen the cross product. Also the cross product you are now very familiar with, because you have seen it in the flux integrals. You have seen it for the surface area. And it's an important construction. It allows us to compute vectors perpendicular to given vectors. And the way how you compute it, you probably have now picked an algorithm to compute that. One way is to compute this determinant. Another way is just multiplying over the cross and write down the new components. So these are the middle term and then the third term. By the way, the middle term, don't forget to take the minus sign if you do it in this way. That's one of the most common mistakes. I will come to the most common mistakes at the very end. Some mistakes you have to look for. And then the cross product is very useful to figure out whether two vectors are parallel. So if you take the cross product between two vectors, it's actually equivalent. Two vectors are parallel if and only if their cross product is 0. And so the 0 vector is both perpendicular and also parallel to any other vector. So that's parallel. And then we have a very important formula for the cross product, which gives you the length of the cross product. So the direction is given by, it's perpendicular to the two vectors, but the length is given by this formula, by this sign formula. And so this is a nice formula. And it immediately also tells you to interpret this as an area, because the height is v times sinus of the angle. And so you have the base times height. That's the area here we have computed. We have the picture of the area. So this is just this triangle here. This is the height, v times sinus t, base times height. Very useful, the cross product, for computing areas, for computing vectors perpendicular to it. And one application, immediate application of the cross product, not that you have to learn this, but just a little bit advertisement, more advertisement for the cross product. If you express the area in two different ways, so you can use these two vectors, or you can use these two vectors, that's what is done here, and you write down these formulas and you divide them by each other. So you get one on one side, and on the other side you get this, and if you solve this, you get this beautiful sign formula, which you might have seen in high school and just been thrown at you. But that's it's immediate from the cross product. So that's a cross product. And one of the places where the cross product really plays a role, especially in the later part, is for the defining what the normal vector is to a surface, Ru cross Rv, if the surface is parametrized, and also compute the surface area when we take the length of that. And so the orientation also is, it's important, orientation, we will come to that, talk more about that tomorrow. Orientation is always given to you when you have a surface, either by this vector Ru cross Rv, or one tells you what the orientation is. But if nothing is said, this is the orientation, and if it's a solid and this is the boundary of a solid like this football, then you have the orientation is outwards. And one really champion for mathematics and physics is Randall Munroe, who has this comic 6KCD. It's a little bit at the edge. I cannot show everything here, but it has strong language, unusual humor, and advanced math. Anything which is so he has this beautiful picture about using the cross product for finding the orientation. So you have one vector. So you take a book, and then you have the first vector along the front cover, the second vector along the back cover, and the third vector, that's then the spine. That's the resulting vector. That's one picture. The right-hand rule is probably more useful. But there he has another kind of politically not so correct rule, which is the handgun rule, where you have the grip is the first vector, rotated so that the second vector is on the safety latch, and then the resulting vector is shooting in the direction of the cross product. And so just maybe a little bit transcending what we often do in the final, kind of go and mix different topics together. Here's a question which already deals with topics which we have seen in the later part. So we have the curl, and one way to express the curl is using this nabla calculus as the cross product of these derivatives with f. And now you could think, because this is kind of, you know, that is perpendicular to the vectors here, the question is, the true-false question, is it true that the vector curl of f is always perpendicular to f? It's a difficult question, so but maybe if you think about it, this is outrageously kind of strange. You have never seen that. And one of the best ways to also approach true-false questions is by just trying out something. You know, one way is just make experiments and say, if you take this vector is kind of a very important vector, so vector field here, and if you take this vector field, which for which we can really compute the curl nicely, so that's a vector field which rotates around so rotates here around, right? And the curl of f is a vector which then points upwards here, so you can compute this. So it's 0, 0. Then you have qx minus py, which is 0, 0, 2. So that's the curl points upwards. In this case, it's true. The curl of f is really perpendicular to f. But it's not necessarily true. You know, if you take, for example, replace this with 1 here, then what happens is the curl of f is still that, because this is a constant which doesn't matter when you take derivatives. And now it's no more perpendicular. So the answer is false. And one way to see whether answers are false is just take some examples and play with it. But we are aware that the true-false questions are often too hard. It's even often too hard for us. If I make an exam myself, which I have written, I get maybe 18, maybe 19 or so. It's hardly 20. I mean, it's really kind of, sometimes you overlook something. But what I can recommend is just first decide with your stomach. Don't spend too much time with the true-false. Decide with your stomach what is the best. And then after, if you have time, go over the things and look at it more carefully. But the true-false questions are really fantastic to prepare and to punch holes in your, you see where you actually don't understand something. So a little bit punch holes in your confidence can be good to get motivated to learn a little bit more. And so this is a question where you really kind of lose confidence at first. Say, oh no, I mean that's hard, and it's a hard problem. So that's about this, and so that was the answer here. And then, but some things you can really prepare well for, and that's knowing a few things. First of all, these formulas we have now just seen, repeated, the cosine formula, the sine formula. Then there is the projection. Also, this you should know. It's a vector. This is called vector projection. If you look at the first part without the W's, if you just take this here, then you get the scalar projection. And then the volume, that's an important thing, the triple scalar product. And you have seen that later also in the course when we do flux integrals, because we take F and then dot it with RU cross RV. That's a volume, and you compute with this volume, you compute the flux through a surface. So the projection formula actually didn't appear so much later in the course. This appeared in the surface area. This appeared essentially anywhere, like in line integrals, in flux integrals. And but these are the four things, and I think you know that because you have used that now so many times. Also, kind of just a reminder about planes. It was a very long time ago that we have looked at planes, but now with the more general theory that we have parametrizations, we have looked at parametrizations in more general parametrizations. This should be clear that this is a plane, and you can kind of read now what it means. It's 3, 4, 1. That's the initial point, right? And then you have a t here, that's 1, 1, minus 3, that's one vector, which is inside the plane, and you have another vector, 1, minus 2, 1, which is here. So that's how this parametrization has been built, using the initial point and the two vectors inside the plane. And we immediately can give the normal vector here. The normal vector is just the cross product of v cross w. And once you have the normal vector, you can immediately get the implicit equation of a plane. The implicit equation is an equation of the form ax plus by plus cz is equal to b. And these are the coefficients here. And the constant here you get by just plugging in the point 3, 4, 1. And then you get this constant. So you can go forth and back from the parametrization to the implicit equation for planes. And lines, we have in the lines, I should have deleted this because we didn't, officially we don't do that here. I already deleted it in the review sheet, but I forgot to delete it here. So you don't need that. That's the only thing we need for the parametrization of a line. We had a little bit crunch time in the second week. So I decided to cut a little bit, so this was cut away. But this is the parametrization you should know. And also here we have a little bit more theory now. We have more general, this is x of t, y of t, z of t. So we have a general curve, a parameterized curve. And this is a special case when it's everything is linear, and this gives us a line. So that's about lines. And then we have distance formulas, which I think we should just know. We can also derive them. I will derive them again, just so that you don't have to learn it by heart if you know how to derive them. But it's useful to know them. So the point is no problem, right? Point you have done at the very beginning, in the first lecture. You just take the sum of the squares of the differences of the coordinates, and then you take the square root. That's Pythagoras. Here, the point and the line, we will come to this, point and plane, we will come to this, and the line and line. These are 4 distance formulas. And I will come just to this thing. So there's line, line. By the way, there's beautiful implementations in Mathematica of some instruments. So to have one line and another line, we want to find the distance between these two lines. And then we have the problem of finding a distance between a point and a line. And then the third thing is we want to find a distance between a point and a plane. By the way, a lot of nice sports thing. I think I could make a game now from that, from all these mathematical implementations. So let's go through that. So one way to there are different ways to remember it. One way to remember is this distance here is just this length here, qp times sinus of alpha. And if you multiply and divide by the length of v, you get, by the sign formula, you get the cross product. And if you remember this, then it's clear that distance between a point and a line has a cross product in it. So that's the first formula. And then the second formula is the distance between a point and a plane. And again, you can do that by just making a little picture here, the length of this, but this time times the cosine of this angle here. That gives us the distance d. And then we can again make this trick with multiplying and dividing by n, and we get the dot product because of the cosine. So that's one way how you can look at that. And the distance between a line and a line, again, you can look at this triangle, and pq times the cosine of alpha gives you this distance, and you can again make this trick, and you get the formula here for the distance between a line and a line. There are I did that already in the first review. I told you how to see that differently, and I repeat that again. It's kind of a nice way to remember. If you build this parallelogram, and so this is qp and this is v, the vector inside the line, and then you look at this cross product, that gives you an area, and if you take the area and divide by the base length, you get the height. And so you immediately you can kind of remember this formula, but it's just area over base, something you have known since eternity. And the other formulas go similarly. I mean, I showed this already. You take a parallelepiped, and what happens is this triple scalar product here gives you a volume of a parallelepiped, and the height of this parallelepiped, that's the distance. And how do you get the height of a parallelepiped? You just take the volume and divide by the base area. So that makes this formula also very natural, and you don't have to really memorize that. And the third thing, with the distance between two lines, you do the same thing. You build this parallelepiped. It's the same formula. So you have this v is translated here down, and w is translated up. So we have this parallelepiped, and it's again the height. And the height is again just let me just run it again. The height is again just the volume of the parallelepiped divided by the area of the base. And so it should be possible to do that without actually memorizing qp times v cross w, things like that. You can actually just see it. Be aware, I mean, you have seen that in practice exams, sometimes we modify this a little bit. For example, if you want the distance between a sphere and a line, or a sphere and a cylinder, like here. Actually, sphere and this, actually, this is not here. There's one more thing. Maybe that's what comes. You know, maybe that's what's kind of. So what we have here is, and it's always the same thing. You just take the distance between the center, or the distance between the lines, or distance between the, and then you subtract the radius. So these are different situations, which also really are just distance, the use of distance formulas. We do some problems on the blackboard. This is the first problem I want to do. Actually, this is an impossible problem, so I'm actually skip this. So that's the first problem. You remember that the distance between a point and a plane, we also had the vector n here, which is normal to it. And we remember, if we see a plane in a parametrization, then we can find the normal vector immediately, right? So the normal vector is, see that, 1, minus 1, 1. That's the normal vector. And then we can immediately, we know what the formula is. We actually kind of also can think about projecting this onto this, if you like projections. But that's what it is. It's qp, and then the dot product with n over n. And so that's the distance. So let's just put that. So we have minus 2, 2, minus 3, dotted with n, which is 1 minus 1, 1, and divide by the length of n, which is square root of 3. And that we can do in our head. So it's minus 2, minus 4, minus 7 over square. So it's minus 7 over square root 3. So just double check, does this make sense? Good, so that's our first problem. Distance formula, part of geometry, and yeah, I would have now got 6 points. Or so. We don't have got complete 7 points maybe. I don't know, it depends on the grader. If you forget that, that's important. So that's not the answer. So the answer is, if you have a fierce grader, you have only 5 points. So 7 over square root 3, what was the radius? 1. So that's the thing, subtract the radius. Good. So that's the first problem. And so this finished already geometry. I don't want to spend too much time more on this. By the way, that looks a little bit like a snowman. I actually, I've seen so many snowmen. Again, even so, I said in the workshop, I don't want to see any snowmen, but these are a couple of them. But actually, they are pretty cool. Many of them actually. This one has this one is nice. I love that one. This is my favorite. Actually, that was after I complained that, I don't want to. So, by the way, a lot of great things came. You have seen that in the beginning. It was very hard. I have about 1,000 pictures. I spent the whole weekend essentially non-stop with filing these things while watching Star Wars, all the 6 DVDs and Star Wars I watched. But anyway, here are a couple of pictures. Really amazing things. Not everything has really rendered here. For example, here the textures has not rendered. I have still to work on things a little bit. So these are a couple of more. Nice use of textures sometimes. Or here also. Really beautiful stuff. That's why I like it. I see a lot of really beautiful things here. So these are more of this. And even the Eiffel Tower has been built. So pretty cool. And the Bunker Hill Bridge. If I would have to make a kind of a ranking, I don't know, to pick the first 3. Actually, here's more stuff. A lot of Star Wars things also. And if I would have to pick 3 of the best, maybe that was just excellent use of, first of all, it's a real monument, right? It's a real monument in Mexico City, the Monumento a la Independencia. And so this was a file. And I learned a lot from that. It's very beautiful, the use of Bezier interpolation curves. It's very smooth and very simple, and I think it's really kind of sublime, very, very nice. Also nice use of texture here, and really beautiful. And that's come from the architectural, so there's a lot of work here in this bridge. This is not programmed, so I mean, if you look at the code, every line has been put by hand, so a lot of work here. Good, so we come to the next topic, and the next topic is about curves. So we look at derivatives, integration, curvature, arc length, and so let's just go here. And very soon we have a new movie coming on. So that's the places where you movies is a lot of places where you see really motion, velocity, acceleration, and so on, like in this beautiful scene here. Anyway, so we have all these formulas. Let's just, I think on this slide you essentially have everything what you have to know about parameterized curves. So first of all, this is a parameterized curve here in space. And then we have the velocity vector, which is r prime. We have the acceleration, which is r2 prime. And we have then the unit tangent vector, which is just r prime divided by the length of r prime. That gives us a vector which has length 1. And the normal vector is also, that's maybe the hardest to remember. It's this, we take this unit tangent vector and we take the derivative, and then we normalize it again. So that gives us the n. And then the b is easy. That's just the cross product. It's perpendicular to both and has length 1. The curvature, no, it's actually easy to remember. It's just the velocity cross the acceleration. And then because there are 3 dots, 3 derivatives here, you want to have a power of 3. It's kind of just what else? So, so that's the way how I remember it. Actually, a physicist thinks about this in terms of units. With the time, you know, you should have the same number of units. That's curvature. And then the arc length, that's definitely something you should remember well. You take the speed, that's the length of the velocity, and you integrate that up from A to B. This frame is called T and B frame. That's the curvature, and that's the arc length. And I think that's about what you have to know about curves. We will do some problems. Also integration, that's kind of the reverse of taking derivative, is just integrating. For example, you know the velocity, then you can get the position, or you know the acceleration, you can get the velocity, and you integrate again, and you get the position. So you can do that. And let's just do a problem here. It's R2D2 is caught in, I think that there was a scene where it was in this garbage truck hauled away. So we have this acceleration. So R2D2, of course, has an accelerator. So he knows the acceleration. So he can figure out where he is after some time t. So, so here we have that R2 prime t. Actually, I changed my mind here from 0 to sine t, just to make a 1 point. So we take sine t, not this. This is the problem. So we start with this here, just to show you something, kind of. So we have R2 prime. Just write down R2 prime of t. And so in this case, it is just t. And it's always nice to multiply out t minus t squared. And then we have sinus of t. And then we integrate, right? So we get r prime t, and so we take it t squared half minus t cubed third, and here we get minus cosine t. And when you integrate, then you always have to worry about the constants. So now we have to add a constant in such a way that at r prime of 0 is 1, 0, 0. So let's look here. At t equals 0, that's 0. So what we have to add here, just 1. At t equals 0, this is also 0. So we have nothing to add. Here, in this case, that's why I changed it. If you look at this here, at t equal to 0, it is minus 1. But we want it to be 0. So we have to add here 1. So that's our r prime. That's our velocity. And so we have r. Let's just write it down again so that we can. So we have t squared half plus 1, t squared half minus t cubed third, and 1 minus cosine t. So this is our first step. We have integrated. And the next step is to integrate again. And so we integrate again to get r of t. And so we get r of t. So we get t cubed 6. T plus t, and then t cubed 6 minus t to the 4 12th, and here we get t, and then minus sinus t, so we have integrated again. Now, we have to match the initial position at t equal to 0, we want to be at 2, 3, 5. So let's just look here at t equal to 0. This is all 0, so we can just add 2, 3, 5. And we are all done. We have now our formula for the position. So that's how we solve this type of problems. By the way, this is already solving differential equations, which is it's an important topic, but we do that only kind of with this type of questions. Any questions? So let's make a problem. Actually, I was motivated by this a submission here of Andrea about Olympic Frisbee. We have here a problem of a curve, and we want to find the arc length. Let's just make this computation so that we have done an arc length computation. So don't forget, if you compute arc length, we have to compute the velocity. So let's just do that here. So we get minus sinus e to the t times e to the t. And then we get e to the t and cosine e to the t. Mind the chain rule. That's r prime of t. Now don't integrate that. That's one of the major mistakes which is done. When you integrate that, you get just rt back. We want to integrate r prime of t, length, which is the square root of cosine square e to the t, e to the 2t, e to the 2t, sine square. And the cosine square will come back. So then here the cosine square e to the t, e to the t, e to the 2t. So that's the sum here, and then we take the square root and not commas. So we have plus. So that's it. Do you see kind of some patterns? Is sine square plus cosine square is an important thing to remember. Sine square plus cosine square you can factor out. You see that's just e to the 2t. So we get the square root of 2 times e to the 2t, which is the square root 2 times e to the t. And now we have this velocity computed, and we can integrate now from t equal to 0 to 1 of r prime t dt. By the way, just writing down such equations is very, very, very important. If you screw up, you get at least some partial credit. Even if the rest is completely wrong, you might get partial credit for that. And so we have that, and then we have 0 to 1, and then we have square root 2 e to the t dt. That's no problem to integrate square root e to the t from 0 to 1. And so this is square root 2 e minus 1. So that's the arc length computation. Good. So that's the. By the way, I made some research about Frisbee because it's an interesting story. Yale claims that the Frisbee was invented in Yale, but that's just completely wrong. And you see that, I mean, in their emblem it says actually light and truth, but it's more light than truth. And so let's go back in time. Let's go back in time, and actually went to the archives, and I looked up all these old maps. This is from 1775. This is from 1854. This is actually where we are here. And so 1877. Let's go closer. So this is Memorial Hall. That's where we are, right? And you see that here, Frisbee Place. So that's actually pretty cool. So that's already an indication here. So we are here. And so what actually happens, there was a company called the Frisbee Baking Company, so they had these things, and then in 87, 70 or so, they were throwing these things around, and that was the place where the Frisbee was invented. And then there was one student was George Frisbee Hoare, and so that was the moment. And actually can back it up here. If you look at the thing, there was Frisbee was before, and then afterwards what's called Frisbee. That's the place, that's the moment when the Frisbee was invented. And you see those on postcards, and Frisbee became an important politician later, class of 1846. So that was the problem here. Now, about matching. Let me just say something about matching. You might have to match anything, like also curves. What is good to look at is, you know maybe some of the curves. This is a curve you might know, t cosine t, t sine t. It's an important curve. It's this spiral. And you might also, I don't know, see if there is a t here. And if you look at this, t plus 1, t sine t, that's essentially a graph of a function, right? If it would not be t plus 1, but t, it's just a shifted graph. So that's essentially a graph. And you see just one graph here. So that's number C here. That's also essentially graph, but the graph which is turned by 90 degrees. And that's maybe the hardest to see. And so that's this cusp here, which is hard to figure out, but that's what happens as the last element. And I really recommend that you look at the practice exams. There are 12 practice exams, much more than you ever can do. It's impossible to do 12 times 13 problems. But look at them, and maybe if you are unsure about some of the matching thing, they have enough practice to actually do these matching problems. And so we already come to the surfaces. There are two different ways to look at surfaces. One is implicit, and the other is parametrization. By the way, that's a nice Lady Gaga implementation. And that's maybe the Sphinx surface. But anyway, so there are two ways. Parametrization is a kind of an active way what the computer does to draw a surface. Implicit is kind of harder for a computer because it has to figure out where the surface is. So, and we have already seen that in the case of the plane. But there are four type of surfaces which you should know. The first one are spheres. The second one are planes. The third one, surfaces of revolution. And the fourth ones are graphs. So let's just go through them. The planes we have already talked about. We have seen how to go from the parametrization to the implicit case. The sphere, we will look at that just in a moment. That's a parametrization you should just know by heart. No, rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi. Just know it. And then the surface of revolution, which essentially is just r cosine theta, r sine theta, z. And so that may be the hardest to remember. The graphs are the easiest. It's just xy, fxy. Easiest way to parameterize this case. And so here are the formulas. So that's the formula. I really recommend you really know this, you recognize this, because you need that in many places for integration. You need it in these spherical coordinates with a rho here. Then we have already talked about the planes. This is essentially polar coordinates, r cosine t, r sine t. So this is, actually there's a mistake here. This is not s, this is t. This is s should be z, right? That's the second variable. And that's the surface, which we usually have written as xy, fxy, or uv, fuv, whatever you like. So, and here on the left-hand side, you have also almost the implicit description. You know the sphere from the first lectures. You know the plane from the first week. You know this also from early on. This is maybe, you see that just now as cylindrical coordinates, r square is g of c. It's a function of c, maybe the square root of, but it doesn't matter. And this is the simplest but often forgotten case of a graph. And sometimes if you have to match surfaces, or it can help to look at the grid curves. This is a surface you have parameterized in a homework. It's the donut. And so if you don't know what this is, it always helps to look at the grid curves. For example, put s equal to 0, and then you see 3 cosine t, 3 sine t, 0, which is a circle. So you see there is at least a circle as a grid curve. And whatever you change s to, it always produces circles. So there are lots of circles in this surface. And also, if you fix t, you always get circles, right? If t is equal to 0, you get 2 plus cosine s, 0 sinus s, which is a circle just shifted over by 2, which is this circle here. And so you see a lot of circles. Even so, this is not of the 4 types we have seen, kind of a hard thing to spot. Another example is, that's actually what you have seen and most of the surfaces I've seen in the project were of this type, because they look nice, right? If you take a sphere, that's the sphere parameterization, and you just multiply it with something. This means you just make the bump, you make the radius change with theta and phi. Here s and t, I was too lazy to use Greek letters, but you see kind of this, this bumpy sphere. And that's a case which has a couple of times appeared already. It's also not of the standard type, but you can also figure out what happens. For example, when s is equal to 1, you get cosine t sine t, which is a spiral going up. So this is this spiral. And if you change s, the spiral radius becomes smaller. So you have lots of spirals going up. And so these are helix curves. And if you leave t constant and you change s, then you see these lines here moving out. So in general, you're maybe too worried about the parameterizations. This is not, you should focus on the 4 cases which we have seen, and for the rest, just make sure you know about the grid curves, and then it should be fine. Most of the cases, you see that in practice exams, we give you the parameterization. So that's the thing. And then we have also implicit surfaces. I mean, some of the quadrics you have to know. I think they have appeared now quite often, so that you should recognize all of them. So there are the standard quadrics, which are the hyperboloids, and the paraboloids, which is here, and then there are ellipsoids. And then there are some special cases like the cone and the cylinder. So these are the quadrics we have to know. Here are the formulas, which I think maybe to remember this, you should see that the paraboloids always have one of the variables without the square. That's maybe the easiest way to remember that. And the hyperboloids and ellipsoids have everything is squared. So these are important quadrics, and you have that also on the review sheet. You have it in every book. You have it in every. Also, there's a handout on it. So you have a lot of results. I don't think that's a problem. I don't think even you have to memorize it now, because you have to see it so many times. But you should recognize them. I mean, this is especially the saddle, right? Also for extrema, and this one for these are graphs of functions. So these are the surfaces to know. And maybe just to make order, so there are ellipsoids, paraboloids, and hyperboloids, and the special cases. The special cases are actually often the most important ones. They appear a lot in examples. For example, the cone is extremely important in physics, the light cone, or also in geometry, you can get any conic section you can get from the cone. So it's a very important surface. Cylinders, of course, are also very important, as you have seen when you did the Mathematica project to build stuff. And so here are the surfaces. What I wanted to show with this picture is for surfaces, it helps to look at the intersections with the coordinate planes. These are called the traces. And also the intersections with the coordinate axes, which are called the intercepts. So this helps to figure out how they are located, and so that these traces are actually here drawn with different colors. And so this has already finished the surfaces. So we already progressed with that, and actually we are, we are, I think just right in time. So let's continue with a gradient. That's a big topic, which also you have the chain rule, directional derivative, tangent plane estimation. Everything hinges on this notion of gradient. And so let's look at these 4 topics. So first of all, the gradient is a vector, right? So it's a vector which at every point we have attach a vector which is fx, fy, fz. And then we can get the kind of steepness in a direction v by taking the dot product with a vector v, which is called the directional derivative. We have the chain rule. This is always considered a difficult topic, but just remember that's the derivative here, that's the derivative. So it looks like the chain rule you know in single variable calculus. And then we have also this is a very important fact, you know, that the length of the gradient, actually this is no square, that's a mistake here, should not be a square. So the length of the gradient is the steepness in the direction of the gradient. And it's also called steepest descent. And so these are the these are the 4 important things. And then we can use the gradient to do all kinds of things. We can use it to compute tangent planes or tangent lines. We can use it to linearize a function. We can use it to estimate near a point where we know the function. And these concepts are all related and all connected to the gradient. Let's just do some problem about yes, first of all, yeah, that's kind of this slide just shows about tangent line and tangent plane. So really, the shortest way to do that is to compute the gradient, and then you can write down immediately the tangent line and tangent plane. So this is in 3 dimensions. We have ax plus by plus cz equal to d, where d is obtained by plugging in the point, and here it's just in 2 dimensions. Ax plus by is equal to d, where you plug in the point p to get d. So that's the tangent line and tangent plane situation. And it really hinges on this important fact that the gradient is perpendicular to a surface, to the level surface. So this is a level surface, and the gradient here is perpendicular to that level set. And the proof is very easy and uses the chain rule here. Because if you are on the surface, then the function is constant. And if you look at this chain rule here, 0 is the dot product of the gradient with the velocity. So it has to be perpendicular to the velocity. And so that's sometimes called the gradient theorem, or the fundamental theorem of gradients. It's a very important fact about gradients and allows us to do tangent line and tangent plane computations. So let's look at this problem. It's an estimation problem. We want to estimate something. And what we can do is, in this case, we can find the linearization. I think I have still a blackboard here. So what we have is we have a function. We can compute the gradient of this function. You should see the function, right? So fxy is equal to xy squared, and then the gradient of f is equal to y squared 2xy. And so this is the gradient, and at the point we have here is also visible. It's close to 1 and 3, so we can compute the gradient at 1 and 3, which is 9 and 6. And now we can immediately write down also we can compute the value of the function at 1 of 3. So what is f of 1 and 3? We can also compute that. That's equal to 9. So we can already write down our linearization. Lxy is equal to 9, and then plus 9 times. And then we take x minus x0. x0 is equal to 1. And then the second one is 6, and then y minus 3. So make sure that that these parts which you have here, these are constants. These are not functions of x and y. And so that's the linearization. Now we can estimate this at the point which we are interested in, like 0.999 and 3.0004. And so in this case, we have 9 plus 9 times x minus 1 is actually just happens to be 0.x minus 1 is minus 0.001 and plus 6 times y minus 3 is 0.000004. So that's the thing. You can leave the expressions like that, but that's the estimation of this value here without any computer. And we get pretty close to it if you look at that here. In this case, the value which we got here is 8.9934, and the real value is 8.99339. So we are very amazingly close to the real value. And it's an important topic. Maybe you have seen that movie. It's the movie Infinity, which shows Richard Feynman's, it's kind of the book, Surely You Are Joking, Mr. Feynman, which Matthew Broderick has made a movie about. And in this movie, they make a race about computing by hand or computing with the abacus. So they have the first multiplication, and now they make a cube root computation. And also here, the
Go. It's 12.
No. More digits. More digits.
What decimal point? What decimal places? Decimal places.
I don't know how he does that with abacus.
12.0. 12.0.
So he had it about 4 or 5 digits.
4.
So whether the story is true is also not so clear. Feynman was a big showman, and but he was lucky that it was close to 1728, which is 12 cubed, and so he could actually do that just using linearization. And so linearization is very important in science. So you should know about that. Let's look at PDEs quickly. That's a rocket, by the way. It's pretty cool, the fire and everything. So PDEs play a role everywhere. And you should know a few PDEs. Actually, we have decided burgers, you don't have to know, but transport, heat, wave, and Laplace you should know. That's not here. You should know the Laplace equation. So burger should be replaced by Laplace, but it's on the review sheet. And you know it anyway already from the second midterm. But anyway, that's the thing. This is PDEs. Just make sure you know them. You know them well. By the way, I just learned today about Quizlets, and it's kind of funny. There are, if you look at what Harvard 21A, what has been done, there are some true-false questions, I think just ripped from our practice exams. But there is actually here, there is a kind of a little Quizlet about PDEs, which I'm honored that this actually has made it as a So PDEs are important, for example, for physics. Physics, if you look at you can for hours watch in YouTube this slow motion thing. It's all physics. It's all PDEs, partial differential equations. Pretty cool. It's fluid dynamics. This is the Navier-Stokes equation. fire or turbulence, and I think somebody is pouring water into oil here, kind of just, so pretty cool. So there's a lot of cool stuff about PDEs. And let's continue with local extrema and Lagrange problems. And so let's go with that. So you know the second derivative test generalizes the second derivative test in one dimension. You know that this D plays an important role here, which is the discriminant. And you also know that fx6 is important. So these two numbers decide whether you have a maximum, minimum, or saddle point. If D is 0, then you just don't know. And so that's the second derivative test. I think you know that. You just don't forget. Make sure. So let's just do a problem. By the way, we like to kind of combine a little bit from different areas. Also, this problem is from a later area. We have a curl of a vector field, and we want to find where the curl is maximal. So, I mean, definitely know what the curl is, right? So we have to look at that. So first of all, we have to compute the curl. To get a function of two variables. So remember the curl. This is a function of, this is a vector field which has two components. So you know the curl is just qx minus py. So it's x squared y. Right? We have x squared y, that's qx. And then minus py. So minus py means plus 3y cubed. And plus, and then minus 6xy. Did I do it right? It's cruel to start to do the problem with a wrong thing. You solve a completely wrong order. Is this right? Actually, I have it here. So just to make sure that I'm not solving a different, yeah, that's right. So let's just do that with this problem. So we want to, the first step when you see an extrema problem is first of all to realize that it's an extrema problem, and also to realize it's not a Lagrange problem, right? There is no constraint here. So that's important. Don't use Lagrange if it's not Lagrange. So this is an extrema of a function of two variables. So we have to compute the gradient of this, right? So this has to be 0, right? We want to find critical points. What is very helpful is to factor things out. We want to compute D, we want to compute fx6, we want to compute we want to find out what is the nature of the critical point. So let's compute fxx. So fx is given here, fx6 is just 2y, and fyy is equal to 18y. And fxy is 2 minus 6. So now we can compute D. Please don't just, even if you see the answer, don't just put the answer there. Put all the details. The D, compute the D. And so we have 2y, 18y, and then minus 2 minus 6 squared. Is it 2x minus 6? Oh, it's 2x minus 6. Thanks. And so now we have to do it at every point to see what actually happens here. So we see that here it's negative, right? Because that's a 0. When y is 0, that's negative. If y is 1 here, we get 36, and here we get 6 minus, so 36, that's positive, and also here it's still positive. fx6 we can compute quickly. When x is equal to 0, it's minus 6. Minus 6, when x is equal to 3, it's 6 minus 6. Huh. Oh, that's fxy. Oh, sorry, I'm looking at the wrong thing. Yeah. So that's fx. I'm looking at fx6, that's just 2y. So that's, actually we are not interested in this case because these are saddles. And in this case, when y is equal to 1, then we have here 2, and here we have minus 2. What happens if it's positive? Then it's a minimum. Negative, it's a maximum. So that's it. Good. So that's the problem. That's the place where the curl was maximal. maximal. And then we have also seen Lagrange problems. Maybe the biggest problem here is, first of all, realize that it's a Lagrange problem, and second, to solve the equations. But the equations, you should just know what they actually mean, right? So if you look at the constraint, which is blue here, it means that you are at the critical point. At these points we are looking for, you are tangent to the level curve. So here they have the gradients are parallel at this point, at this point, at this point, at this point, and this point. And the second equation gives us just the constraint. So these are the Lagrange equations, and you should also know about global maxima. Global maxima being the whole plane, or if it's a region, then you have just to look at all the critical points on the boundary, critical points in the interior. The constraint has been lost here for some reason. And but you have just to shout the answer. The first one who shouts the right answer gets, and with the right explanation gets a chocolate. So 3, 2, 1, and 0. Does this have a global maximum or a minimum or none? Who said minimum? Why? Because even powers, and then but there is even powers in the x square y square, which is negative, but that is powers are high. Yeah, okay, so you two together get so yeah. So the powers are lower, right, for the x to the and can you pass this over? Yeah. So in this case there is a global minimum, right? Because these powers here dominate in the large. This goes to infinity, and that has a smaller power. For example, take x equal to 1,000, right? You get here, you get x to the 18. I mean, you get huge, and this is only x to the 6, x to the 12. So that's much lower. So that's about global extrema. And so I have another problem. I have a lot of chocolate here. So another problem, 3, 2, 1. You know this. What can you say about the critical points of F? Minimum? No. No. They are? No, not maximum. What? Nanosaddles. Yeah, nanosaddles, that's right, yeah. That's right. So why is this true? Yeah, who said that? Who said nanosaddle? Can I throw you? Oh, sorry. So why is this true? So let's look at that. What do you know about D? So D is equal to fxx fyy minus fxy squared. Now we know from this equation, this is by the way a partial differential equation, we know this is 2fxy squared. So this 2fxy squared minus fxy squared. So this is fxy squared. And actually this is bigger or equal to 0. So actually it could also be 0. That's why the answer that it has is not a saddle is really the right answer. Not the maximum necessary, not the minimum, not the maximum or minimum, so no saddle. Cool. Does it make sense? Good. So that's the, let's do an extremer problem. So we have a C3PO has a, it's kind of a schematic thing. And then we have a problem, we have a function which we want to extremize, which is actually just the area of that thing. And then we have a constraint. And let's just quickly do that so that we have done a Lagrange problem. I'm SpongeBob. No, it's not. So let's see. So first of all, you have to remember the Lagrange equation. So we have to take the gradient here. So fx, which is 2x. So we can write down the Lagrange equations. Fx is equal to lambda times gx, which is lambda times 4. And then we have Fy, which is 2y pi. And then we have lambda times, and then 2 pi. And always write down also the constraint, which is 4x plus 2 pi y is equal to 1. So now we have everything together. We have these 3 equations. And the best way to get to solve this is get rid of lambda. One way to do that is multiply over the cross, so divide out. So we take the first over the second without canceling anything except constants. So we have x over y pi is equal to 2 over pi. And then we multiply out. So we get pi x is 2 pi y. Pi goes away, x is equal to 2y. And that's what you always have to look for. You want to have a relation between x and y. And once you have that, it's easy because you can just plug into the, into the constraint. And you plug this into the constraint, and then you get 8y plus 2 pi y is equal to 1. And then you get y is equal to, and so on. So you have no problem anymore. You're over the hill once you have this relation. I have to accelerate a little bit, but I don't think that's a problem. If you just make more problems, solve more problems on your own. There was a problem I wanted to do about the Death Star, but I have to scratch this. It's a problem with 3 variables. You can do Lagrange with any number of variables, and it's no problem. It's always the same thing. And we have to do double integrals and triple integrals. You have already done that and repeated quite a bit in the later part. But let me just repeat a few important points. So first of all, make sure you use the right coordinate system. And also look whether you use a type 1 or type 2 integral. Possibly switch from type 1 to type 2. And then really important is make always a picture to really set up the integral. And usually, what you have is that for the type 1, you have a lower function and you have an upper function. And for a type 2, you have a left function and a right function. And also remember Fubini. Fubini tells us that for rectangles, we can interchange nicely, but that's only for rectangles. And these are the type 1 integrals, type 2 integrals. So we have a type 1, we have a lower and an upper function. And for type 2, actually, type 2 would be better to be called left to right function, left to right integrals, and these are bottom to top integrals. So these are the 2 types. And so for switching the order of integration, it's really very important to make a picture. Here is an example. This is a prototype example where we cannot, and I think I have done that already. You might have seen that in lecture. That's the prototype example par excellence, where we are stuck here with the integral. But you can still do it by switching the order of integration. And then if you write it, this was a type 2 integral. Now let's write it as a type 1 integral. Then you go from 0 to 1 dx, right? And then you go from 0 to x dy. And then you have still e to the x squared. But now there is no problem that gives us e to the minus x squared, e to the minus x squared times x. And now you are safe, right, because you get e to the minus x squared over 2 from 0 to 1. And so you get e minus. And so you get e minus 1. So you get 1 minus 1 over e half, I think. So that's the prototype example. And here's, so that was the thing which I've just have written down. This is another problem. And I think you have a lot of problems like that. You have also in the second midterm, you have done such problems. But still, there were some in the second midterm who didn't do the switch, the order of integration, and then you were stuck. So in this case also, what you have to do is just set up the integral or the picture first, make a picture here. And you see it's a type 1 integral from 0 to 8. So you just draw what is written there. And then it goes from x to 1/3 to 2. X to the 1/3, actually x to 1/3 goes the opposite. That was not good. X to the 1/3 is going opposite. X to the 1/3 goes like that, and then goes up to 2. So that's 2 here. And so we have this integral here. And now we can change the order of integration. We integrate from 0 to 2 dy, and then we integrate from, it's a left to right now, from 0, and then we have a y cubed here. It's x equal to y cubed, and then cosine y to the 4 plus 1. And now we are safe, right? Because once you solve the inner integral, which is no problem. So this is actually dx here. Once you solve the inner integral, you get from 0 to 2, and then a y cubed cosine y to the 4 plus 1 dy, which can be solved by substitution. So that's also an important, actually that, yeah, y is equal to 2 here, the 2. And polar coordinates, just make sure you remember polar coordinates. If you have a region given in polar coordinates, then when you integrate in polar coordinates, don't forget to include the factor r here. So actually, I have only a couple of minutes. Just don't forget the factor r. And maybe surface area and arc length. Actually, just that you don't, you have talked about arc length. The surface area formula is just a formula you have to know. And it's easy to remember if you remember this is an area here. And so this is an area of an infinitesimal parallelogram, and then you integrate that up. And so once you have set this up, you get actually just a double integral. And it should not be difficult to do. This is an example of a problem. So first of all, in this case, the problem is maybe just to find a parametrization of this surface, right? And so it's a graph of a function, and so it's just x squared plus y squared. So this is r of x and y. That's the parametrization. And then we can compute Rx and 1, 0, 2x, and we can compute Ry, which is 0, 1, 2y, and we can compute the cross product Rx cross Ry, which is equal to minus 2x minus 2y, 1. And the length of this, we have then just to integrate over the circle, the square root of 1 plus 4x squared plus 4y squared dx dy, which is now just a double integral. And this double integral, if you look at that, it's very clear that you have to go into polar coordinates to solve this. And then you get the factor r, which helps you to solve this problem. maybe just at the very end about the top
classic algebra
top mistakes.
Let's see what they are.
There is a
Now, we're
nice
gonna start
YouTube
pretty
video
fast.
by
Let's
Ed
take a listen.
Berger.
Coming in at number 10 is the old classic
Look at
squaring
that.
the
It
negative
actually
mistake.
also happens
A
in
minus
21A.
squared, unless it's been snared. Great lyrics, great song. Coming in at number 10. Number 9 is that classic country, the log mistake, with those great lyrics. A log of a sum is not the sum of the logs. Let's take a listen to that little peek right here, right now. The log.
Anyway, so you have to look at that. And so in 21A, just a list of nonlinear linearization. Number 1, division by 0 in the case of Lagrange. We have just done that. Not trying an integral theorem, that's a very important thing. Especially tomorrow we will do that. Lack of figure integration, that's essentially a guaranteed mix-up of dimensions for graphs. Forgetting the -1 in cross product, that's the middle term. Don't use these for line integrals, that's a source for mistakes. Forgetting integration factor, the R factor or the rho square sine factor, we will talk about this tomorrow. Wrong orientation, small mistake, don't worry too much about it, but get that. And the last one is not writing down the result. So that's the last thing. And tomorrow we are looking at the second part, episode 2, the attack of the integral theorems. And so that's it.